Okay, so in section 2.7, you learned about, again, using the definition of a derivative to find the f prime of x, which is a derivative function. And you'll have, you've seen some examples of that. But once we know what the derivative is, what f prime of x is, let me just make that a little bigger. The question is, can we say anything about the function? Okay, so in other words, we're going to be looking at the derivative f prime of a function and seeing if, based on the derivative and even the second derivative of a function, what does that tell us about our original function? There are no formulas here. There are no formulas. This is conceptual. So let me give you a moment to copy this down. Okay, to copy and I had to use a little bit smaller font because below we're going to have a actual picture here that we're going to use. We want to sketch a possible graph of a function f that satisfies these three conditions. Conditions A, conditions B, conditions C. All right, so let me give you a moment to copy that down in your notes. All right. So let's see here. Let's examine these conditions. All right. The first condition says that the derivative is greater than 0 over the interval from negative infinity to 1, not including 1. So can we, what would that mean about the function? I mean, what does this mean about the function when the derivative is 0? What is that telling you about function f? Well, Neil, you can have a function that is actually negative, but yet its derivative is positive. But that's right, Sebastian. The f is increasing. Okay, so I'm going to try to draw this as best as I can. Write this, I should say. That means f increases. Wherever the derivative is positive, the function increases. So the function increases over the interval from negative infinity to 1. Okay, because remember, when you have function f that is increasing, then if your function f here is an increasing function, that means then that the tangent lines, I know, Yaki, I don't want you to see the other part yet. I don't want you to see the other part. We'll get there, no problem. Thank you, Yaki. So here's a function that's increasing. What can you tell me about the slopes of the tangent lines where the function increases? The slopes are what? The slopes are, well, I guess, I want to say, but so are the slopes positive or negative? For this little function, this little thing that I drew here. Hold on here, let me just get this. Hold on, let me get it in black here. That's right, John, that's right. Yeah, the slopes are positive because the tangent lines, lines have slopes. The slopes either 0, does not exist, or positive or negative. These slopes of these tangent lines have positive slopes. The tangent lines, that's okay. I want all answers, okay? No problem, Betsua. Well, if the slope of a tangent line is positive, what tells you about the derivative then? If the slope of the tangent line is positive, then the derivative would be, that's right, Yaki, positive. And so saying then that f prime of x is greater than 0 just means that the slopes are great. The slope, if the derivative is greater than 0, the function then therefore has to be increasing. Now you have the other situation where you could have a function that is decreasing, a function like this. Okay, a decreasing function. And hold on here. And I might wonder, well, how does its derivative behave for this decreasing function? Let me pick a couple of points on that decreasing function, and let me draw a couple tangent lines. Here's a tangent line. Here's another tangent line. Okay, what are the slopes of those tangent lines? Are they positive or negative? Negative. So a decreasing function has the derivative is negative. Okay, so let me just switch here. I kind of like using this mouse. I don't know. I know there are other ways, tablets and things, but it is pretty. I don't know if a tablet would give me this functionality. I just have to try to write neat enough, So when f prime of 0 is less than 0 on 1 infinity, on that interval, that means that our function f has to decrease. Our function f decreases. On the interval from 1 to infinity. Okay, so we've taken care of the first condition. Are there any questions on that? All right. Well, let's look at the second condition. Here in the second condition for part B, they talk about f double prime of x. Okay, f double prime of x being greater than 0. So in part A, the first derivative tells you where the function increases or decreases. But what does the second derivative tell you about the function? Concavity. That's right, Sebastian. Concavity. And basically, what you're doing is, if the second derivative is greater than 0, remember what the second derivative is. The second derivative is the derivative of the first derivative function. Okay, this is kind of brief notation here, but what we're doing with the second derivative is we're asking, well, how do the slopes behave? Are the slopes increasing with x? Are they decreasing with x? And like in the first picture here, where I drew this increasing function f, I've drawn some slopes. What do the slopes do with respect to x? Do the slopes increase with respect to x, or do they decrease? For this first picture here, I've drawn a couple of tangent lines. We have positive slopes for both tangent lines, but are the slopes getting larger or smaller as x increases? I mean, I didn't draw like an x-axis, but we know there's one there, right? They're getting larger. They're getting larger. So that means then that since the slopes are increasing, that means the second derivative would be positive. And this means then, what this means is that our function f, because we're trying to learn about our function f is what's called concave up. Concave up. And you can see that in this picture, the function f here is concave up. We call that, by the way, C. Well, I don't want to clutter things up, but the function f is what we call CU. I don't want to get things cluttered. CU means concave up. CU means concave up. And if you think about your hand, the palm of your hand, if you like hold it up, it's concave up. Okay. Now, incidentally, the second derivative is negative over negative 2 to 2. That would mean then that I want to say it's the right way, the derivative of the slopes is negative. Okay, the derivative of the slopes is negative, and so the over negative 2 to 2, f would not be concave up, it would have to be concave what? Would have to be concave down. Good. Good. Concave down. Good. Thank you, everybody. So here's another now this function also, by the way, is concave up. But I want to just show you a picture of a concave down function. Okay, so let me draw one right here for you. All right. This function f is, f is concave down. Were to draw a couple of tangent lines, what's true about the slopes of the tangent lines in that for our function f? Naturally I have an x and a y axis, right? Yeah, the slopes, good Kelvin, good Ian, the slopes of the tangent lines are decreasing with x. They're decreasing with x in this picture here. And so that's a concave down function. That's a concave down function. And incidentally, another concave down function would be a function like this. This function is also concave down. Because slopes of the tangent lines are decreasing. Okay, so these are properties of functions that you've not learned before. In the past, what you would do is you'd have your function, and it would be maybe a fairly simple function, and you'd graph it on your calculator. You would find things about asymptotes. You might talk about where the function's increasing, decreasing, but you didn't talk about concavity or the first derivative. See, in order to understand functions better, how they behave, we need more ways to evaluate the functions, and that's where these first and second derivatives come into play. Incidentally, the last two, what's the third condition mean? This third condition here says the limit of the function as x approaches negative infinity equals -2. That's end behavior. And what's going to happen if the function is in the limit is approaching -2? What kind of asymptote would that be? Would it be a vertical or a horizontal asymptote at -2? It would be y equals -2. It would be a horizontal asymptote. That's right, Sebastian. That's right, but Betsua. That's right, Trevor. Okay, and then there's going to be another asymptote on the right as x goes to infinity, okay, at 0. But, so now that we understand what these conditions mean, are there any questions? All right, well, now what we want to do is we want to graph this function. Okay, we want to graph the function based on the 3 criteria. And these kind of problems you have to be careful with in WebAssign because they're usually multiple choice. And of course, you know, on the homework, if you have 4 tries, you get 2 attempts, right? But that's on the homework, right? Exams were a little pickier. So, all right, take a moment to copy the graph down. And what we're going to do is we're going to draw our function. I've just drawn the XY axis and a horizontal asymptote at -2, but we'll have to draw in the function. Okay. Now, people will approach this in different ways. But what I'd like to do, and you know, they're not even telling you what points are on this function. I mean, we don't have coordinates of the function, right? How many are really used to having coordinates of a function to graph the function? How many are very used to that? Sure, Joe is, but now that you know calculus, you can graph a function. Now granted, there could be multiple functions that satisfy the conditions above, but we can at least get an idea of what the function would have to resemble. So what I like to do, and I actually did this problem from scratch, just like a student would, and what helped me first was to work with the asymptotes. So I want to put a point right here. Okay, because I know that as x approaches -infinity, well, Sebastian, before calculators, they did use this to help them. Absolutely. Absolutely, they use this information to help them graph functions. And even the calculators, yeah, I mean, the calculators graph like 1,000 points, and so, but absolutely. But even the calculator graph sometimes doesn't show you everything. You'd be surprised. And you can't always zoom in on everything. But what I'm doing is I'm drawing a couple of points. I'm drawing a point here. Maybe I'll put it in red. Drawing a point there, and then I'm going to draw a point over here. And I'm going to require that my graph pass through those points. You notice the point on the left is very close to the asymptote, horizontal asymptote, y equals -2. That's because as x approaches -infinity, and I'm going the axis, x-axis, I'm going out to where x is very negative. Okay, the limit as x approaches -infinity of our function is -2. So that handles that requirement. And then the other requirement, as x gets very positive, as x approaches infinity, the function will approach 0. Okay, so I'm just kind of, I want kind of to orient myself. And by the way, this takes care of the third condition. Now we have to work with the other conditions. So we know that by part A, the function increases on -infinity to 1. Okay, the function increases from -infinity to 1. Okay, and but then it decreases on 1 to infinity. Okay, so Well, I'm going to draw an increasing function here. And again, I'm gonna choose to let it pass through -2, 0, or close to that. The function's increasing. The function's increasing. But does it increase? Does it increase? Well, hold on. The function increases, but also it has to be concave up from -infinity to -2. So this function so far increases, and it's concave up from -infinity to -2. Okay, so I can sort of maybe mark off the conditions, taking care of these conditions here. I've taken care of this concavity condition. Okay, but after -2, when you're between -2 and 2, the function f is concave down. So that means I gotta draw the function here to have it be concave down. It's still increasing because it's supposed to increase till I get to x equals 1. So it's still increasing, but it's concave down. Still increasing, but it's concave down. Okay, but then when it hits 1, it has to start decreasing. Okay, so the function changes concavity at x equals -2. It goes from concave up to concave down. And then when it reaches 2, it goes concave up again. So it's going to have to do this. Okay, and that's what the function's going to look like. That resembles the function. Now you could have the function be higher, taller, but it's going to have whatever it is. It's going to have resemble that, have that flavor to it, so to speak. Are there any questions? I mean, we'll move to the next question then, if you're comfortable. And of course, you do have the recording. You'll have the recording to refer back to. How many think this is kind of cool? So, all right. So John, what I'm doing is I'm drawing a function that'll satisfy the 3 requirements above. So the concave up, you'll notice from -infinity to -2, the function's concave up. Think about your hand, the palm of your hand pointing upward. Look at the shape of your hand pointing upward. That's concave up. And then from -2 to 2, the function's concave down. Palm of your hand points downward, concave down. Okay. And then finally, from 2 to infinity, function goes back to concave up again. And of course, the function increases from negative infinity to 1. Function is increasing. But then from 1 to infinity, the function's decreasing. So when you do these kind of problems, you have to, look at your graph carefully. Let's see, Ian says, is the first derivative always when it's increasing versus decreasing? That's correct. First derivative tells you whether the function's increasing or decreasing. And the second derivative tells you whether your function what its concavity is, whether it's positive or negative. And I'll mention another thing too while I'm at it. This point here, this point that I drew, where the concavity switched from concave down to concave up, that's known as an inflection point. That's called an inflection point. Sebastian, the third derivative, let me see here, one moment. I think it's about skewness, but let me just check, one moment. Let me go to Google real quick. Interpretation of third derivative. Really what we work with is, at least for graphing, we work with the first and second derivatives. The third derivative, in physics, the third derivative of a position function is what's called the jerk function. But that's using vectors. But I think also it can be regular, like scalar functions. But I'm not going to worry about that. But for graphing, the first and second derivatives are what you need to worry about. Good question. Good question. Okay, well, let's move on to the next example then. All right, so here we go. All right. We want to describe a function whose derivative f prime is below. Now, what you can do, I'll give you a little time here. You're welcome. How many want to copy this graph in their notes? How many want to copy that down in their notes? Actually, you may not write the whole grid, but okay. John, Rodrigo, that's fine. Let me give you a little time to copy the graph in your notes. And obviously, you don't have to use all the grid lines. You know here that let me see here. I want to make it show. Blue kind of works nice. You know, this is your x-axis right here, and this is your y-axis. Okay. So, all right, let me give you a moment to copy that down. Okay. All right. So, well, what is the first derivative give you information about in regards to the function f? What immediately would a first derivative give you information about? That's right, John, whether the function's increasing or decreasing. And it also can give you even more information than that. But what they're doing here is they're drawing the graph of not the function, but the first derivative. Okay, the first derivative. Now, from, let me see here, I want to do this. Yeah, this will do. From 0 to 2, let me see here, one moment. I'm going to be a little bit careful here. Okay, so from 0 to 2, when x is between 0 and 2, what's true about f prime? Is f prime positive or negative? That's right, Ian. The f prime is positive. So you're not going to draw tangent lines to f prime. They're giving you the graph of f prime, and the f prime is the function is above the x-axis when x is between 0 and 2. So f prime is positive when x is between 0 and 2. What other x values is x prime positive at? That's right, Yaki, 4 to 6. That's right, Sebastian and John. 4 to 6. F prime is also positive. So that means this function f has to be increasing when x is between 0 and 2 and x is between 4 and 6. It has to be increasing. Oh my goodness. Oh my goodness. You're right. I forgot about that, Sebastian. From 8 to infinity, the function's also, the derivative is also positive. So the function increases over the interval 8 to infinity also. Now, where would the function decrease? Where would the function f decrease? Over what interval? Or intervals? Well, when a function decreases, what's true about its derivative? A function f will decrease when its derivative f prime is negative. That's right, Yaki. Well, between 2 and 4, the derivative function is negative. And between 6 and 8, the derivative function is negative. Therefore, we can say that our function f increases on the intervals 0, 2, and 4, 6, and 8, infinity, since f prime is greater than 0, 0 on those intervals, but f decreases on the intervals 2, 4, and 6, 8, since f prime is negative, less than 0 on those intervals. Okay, so let me give you a chance to copy that. And are there any questions? All right, well, now I'm going to mention something else too. When we describe a function f, we need to talk about where the function has a maxima and minima. So we know that this function here, well, the function's going to have a local maximum at x equals 2 and x equals 6. And the reason, like, let's focus on the x equals 2. Hold on, I got to get the shape off. Why does the function have a local maximum at x equals 2? Well, you know, what is a maximum? Okay, if you have a function f here, and it looks like that, the maximum is the highest point. It's not the highest rate of increase, it's like a mountain, it's like the top of a mountain. This is a maxima here. This is a local maxima. In that little, and I'm not saying f, well, I want to be careful because I don't want to confuse, this is just kind of an aside, but this is a local, it's what's called a local max. Okay. And it says that the function increases on 0, 2. Okay, but once it gets to 2, it decreases. So at x equals 2, I mean, if this is your x-axis, it's 2, you know, the function increases. And I got to be a little bit careful here. This little picture here is just to show you like an example of what a local max is. But they're saying the function increases on 0, 2, but then it decreases on 2, 4. So it goes from increasing to decreasing at x equals 2. That's why you have a local max at x equals 2. Similarly, there's a local max at x equals 6 because the function goes from increasing to decreasing at x equals 6. Now we can also do a local minimum. Okay, if you have a function that does this, the very bottom point here is called the very bottom, the bottom of the valley is called a local min. Okay, local minimum. And since our function here, our function at x equals 4, well, the function decreases from 2 to 4, but then it increases from 4 to 6. So at x equals 4, you have to have a local minimum. Similarly, at x equals 8, there's another local minimum. Yaki, I'm not even referring to concave down or concave up here. I'm just drawing a couple pictures where I have the bottom of a graph and the top of a graph. That's really what I think of local min and local max. All I need to know to determine the local min and local max is where the function changes from increasing to decreasing and changes from decreasing to let's see, for local max, local max would be where the function increases and then decreases. A local min would be where the function changes from increasing to increasing. So I'm not even worried about concavity. And yes, John, the local max and min are the values of x. So I'm thinking, you're going to have a similar problem in your homework. And so this is why I'm doing this problem with you. Okay, are there any questions, any more questions so far before we move on? Okay, well, let's get to the next, there's more information that we can talk about, more characteristics of this function. What's a characteristic that we haven't talked about yet for this function? Because, we got to graph it. We got to graph it, so we need the most information we can get here. We know that where the function's increasing and decreasing. We know it's local maxima and local minima. What else is important? An important feature for a function that you have learned in calculus? Well, asymptotes are important, but I'm not really worried about asymptotes here. Something else begins with a C. A functions. Well, okay, John, continuity is important. It's let me give you a little hint. C-O-N-C, concavity. There you go. I want to know about the concavity of the function. So let me go to the next slide here. And what I'm going to do here is I have the function. And, well, no, I have the derivative. I have the graph of the derivative. And what I'm going to do here, hold on, just trying to kill a mosquito. It's these mosquitoes, they're like stealth fighter planes. So you can't, they fly close to you and then you can't get them. How many have noticed that? Okay, Joe knows what I'm talking about. Okay. All right. So let me see here. But I get this guy, but I don't want it to interfere with my lecture. All right. I'm not going to let him bite me. All right, but let me continue here. Yeah, Lynn, I hear what you're talking about. All right, so I have the graph of the derivative here, and what I'm going to do is, concavity relates to the second derivative. The second derivative is the derivative of the first derivative. So I'm going to draw some tangent lines. Okay, I'm going to draw some tangent lines here, and you can draw them on your picture. You don't have to redraw the picture again because you drew the picture once already. What seems to be happening with the tangent lines up to the point x equals 3. If we go from 0 to 2, and look at the tangent lines of our function, are the slopes of the tangent lines increasing or decreasing? And actually, hold on, let me get one thing here. So the tangent lines drawn on our derivative function, okay, the tangent lines, now let me see, one moment here. I think maybe, no, hold on. Let me erase that. Let me scratch that. I don't need to be that complicated. I don't need to be that complicated. And actually, that may not even be, you know, well, I'm going to blame the mosquito on that, okay, for interfering with my thinking. Here's 0 to 3. Here's 0 to 3. And we look at the f prime. We look at f prime here. What is f prime doing, that derivative function from 0 to 3? What is the derivative function f prime doing from 0 to 3? It's decreasing. That's right. So that means then that from 0 to 3, the function has to be concave down. Okay, because in concave down, I drew a couple of, again, a couple of pictures of what concave down is. Concave down is when the, you have a concave down function f when the slopes of the tangent lines to the functions are decreasing. And these are two instances of that. But you don't really need these pictures here that are checked because the graph of the derivative, when the derivative is decreasing, the function's concave down. Now, what happens when the function? What happens when the function from 3 to 6? From 3 to 6, what can you tell me about the first derivative function? It's increasing. And so if it's increasing, then from 3 to 6, it's concave up. That's right, Lynn. Okay. And also notice that the function, the first derivative function, increases from 6 to infinity. And so the function's concave up there as well. So this then gives us a third aspect. Okay, a third aspect of the function. Okay, so really all you need to copy here is the function is concave down on 0 to 3, since f prime decreases on 0 to 3. And also the function is concave up, cu, on 3, 6, and 6 infinity, over those intervals from 3, 6. Did I get them? Hold on. I'm going to get this thing. It's on my hand. It's ready to go. All right. This will be an interesting recording class. All right. So, okay, are there any questions on these comments here? All right. A few more things we can mention then. A few more things we can mention. May I go to the next page? Are we good? All right. A few more things. So we know there's a point of inflection at x equals 3 because the function goes from concave down to concave up. It changes from concave down to concave up at x equals 3. And basically now we're ready to try to graph the function. We're ready to try to graph it. So let me let you copy this down. and then we're going to go to the next page and graph this function. Hold on. All right. So I'll go ahead and move to the next page. We're good. Okay, I'll wait a little bit. So now when we graph this function, one moment, Trevor, hold on. Let's make sure we're good on this page, and I'll go back. But all right, so there, I guess you do need to copy 5 as well, because if f of 0 equals 0, see, we're going to have to, Trevor, is your question on something about copying, or is it a conceptual thing? Okay, all right. All right. Let me finish the problem, and then I can backtrack. Okay. All right. So we are ready to graph, but you know what we have to do. Like in WebAssign, you will get like a they'll give you a choice of maybe 4 graphs, and they'll say which is the right graph. Okay. For this problem, since we don't have a you know, you have to be given some little bit of information to well, I want to say this the right way. Actually, you don't, but we're gonna assume here. Let's suppose that f of 0 equals 0. Let's just suppose that. Okay, we don't need to suppose that, but we're going to suppose that here, because you know, for the graph we're going to draw, we're going to suppose that the graph passes through the origin. All right, so now at this stage we're ready to draw the graph. So the graph, okay, is going to look, let's see here. It's going to pass through the origin, and the graph has to be increasing from 0 to 2, but it's concave down from 0 to 3. So it's concave down from 0 to 3. Okay, so I'm going to draw a graph that's concave down from 0 to 2. Okay, but then it decreases on 2 to 4, but it stays concave down. You know, it starts to decrease here. Okay, but it's still concave down. See what I'm doing? It's still concave down. Okay, so the graph increases from 0 to 2, and then decreases on 2 to 4, but it's concave down up to 3, but then it's going to switch to concave up at 3. Okay, so I'm trying to draw some like key points here. Maybe I'll put them in red. Okay. The graph switches to concave up at 3. Okay, it switches. But then it increases from 4 to 6. So it increases from 4 to 6. And it stays concave up. It stays concave up until you get to 6. All right. And there's going to be a cusp at 6, at x equals 6. Why would that be? Why would there be a cusp at x equals 6? Well, look at your derivative. What happens to the derivative when x equals 6? What happens to your derivative function? Look at your graph of f prime here. It jumps. That's right, Lynn. The derivative equals, let me see here, equals positive 3 when you approach 6 from the left, but when you approach 6 from the right, the derivative equals negative 2. Okay? So the derivative switches from positive to negative at x equals 6, but it doesn't do it in a smooth way. The derivative's not continuous at x equals 6, and so there's going to be a cusp. Right, the limit, Lynn's right, the two-sided limit does not, the derivative, which is a two-sided limit, doesn't exist at x equals 6, because the derivative function goes from positive 3 as you approach 6 from the left. The derivative approaches positive 3, but then if you approach x equals 6 from the right, the derivative function here approaches negative 2. And so there's going to be a cusp, but then the derivative, the function stays concave up from 6 to infinity. The function, I should say, the function is concave up. Okay. So this is what your function f is going to look like. That's a possibility. Okay. And I'm putting in the sort of the key points there. This was 3 here. How many think that's absolutely cool? Yeah, I like it, Nicholas. Rodrigo likes it. John likes it. Anna likes it. Good, good. That's good to hear. Good to hear. All right. All right. Well, we should do one more. We should definitely do one more, so that the homework is well represented. with the examples. Again, the book has examples, but I'd like to do one more. Are there any questions before we move on here? Trevor, I'll bring that back during, we'll have a little classwork time. Let me bring that example back, okay, during classwork time, this second example, so you can copy what you need to. Does that sound good? Okay. K means okay. All right. I'm learning about these texts. All right, I'll move to the next example. Everybody's good? All right. An antiderivative. Oh my goodness, an antiderivative. You've been learning about derivatives, and now we have something called an antiderivative. All right, what's that about? All right, so let me give you a moment to copy this example down. Okay. So an antiderivative is, it's not as scary as you might think. What does an antiderivative mean? Well, I'll make a little note here that if you take the derivative, okay, if you take the derivative of an antiderivative, what do you think that's going to give you? That's right, Ian, the function f back. If you have the antiderivative of a function, if you have the antiderivative of a function f, and you take its derivative, that's going to get you the function back. It's like matter and antimatter, you know. Okay, so this is right now, this is understandable to you, that the derivative of an antiderivative equals the function f. And the antiderivative is a function of x also, you know. Now, in this problem, we're going to assume that the value of the antiderivative when x equals 0 is 1. And what we want to do is sketch a possible graph of our antiderivative f, our antiderivative function f. And you know, when we put f, big F there, we're suppressing the x. But we understand that our big function f is a function of x. Our antiderivative function f, the capital F function, which stands for antiderivative of our little function f, that antiderivative function is a function of x. So, you know, little f, lowercase f, when you see that, that means f of x. Big F, that means it's an antiderivative. We use that for antiderivative, but that's a function of x as well. Okay, so I'll go ahead and, well, are there any questions? Are there any questions? Okay, well, let's move then to the example. Let's move to the solution, I should say. So what I've done is I've drawn the function f again, and my solution is going to be here. All these problems involving graphs are designed to help you understand the derivative better. And when I see if this is a function f of x, so this is an f prime of x. This is our function f. And what I'm going to do is what I always like to do. I like to draw tangent lines on my function. Well, actually, hold on. Now, hold on. Before I do that, let me think a little bit here. Let me think a little bit. Let me make a note here. Hold on. I did this fine, you know, and I did these problems like cold turkey, as we say. I did them like a student would do. Granted, I have a little more experience than you, but I'm going to make that note again that the derivative of the antiderivative function is equal to my f of x function, which is graphed here. Okay. The antiderivative, well, yeah, we want to draw a graph of the antiderivative function. But in order to do it, we need to recognize this fact that the derivative of the antiderivative function, will give you back your original function f. So I notice here that the function f, when you draw the function f, you know, f here is always what? My function f is always blank. Looking at the graph. Function f increases, then decreases, and increases again. But it's always, the word I'm looking for begins with a P. We'll do a little Wheel of Fortune here. Positive, good, good. How many love Wheel of Fortune? The game show. Okay. Well, so Ian, you're on the right track. Because our function f is always positive, that means that the derivative of our antiderivative, that would also be always positive. And so when I draw this function, which we said that f of big F of 0 equals 1, the function has to always be, the capital F function has to always be increasing. It has to always be increasing. Okay? But something happens at 1. I mean, I can draw my capital F function to be increasing. That's fine. I want to do it the right way here. But when we hit x equals 1, okay, when we hit x equals 1, something happens to the function. What happens to the function at x equals 1? The function goes from increasing to decreasing. Well, that means that our derivative would, I want to say this the right way. Hold on here. I want to say this the right way. Okay, I'm going to put the 3 here because we know that's another important point, right? Because at 3, the function goes from decreasing to increasing. So I want to say this the way I want to say it, but I don't want to erase what I got here. Let me just kind of. What I guess I want to do is I want to draw tangent lines of my antiderivative, because I know that the function's always positive. So the derivative of my antiderivative is always positive. But that means the tangent lines are always going to have positive slopes. This is how, when I did this problem, this is how I did it. Okay, so I drew some tangent lines. And I notice that when x is between 0 and 1, the function increases. Well, that means that the tangent lines for my antiderivative will also increase. They also will increase up till x equals 1. When x equals 1, after x equals 1, the tangent lines, the slopes of the tangent lines have to start decreasing. They have to start decreasing. So in other words, the function f of x increases from 0 to 1. So that means the slopes of my tangent lines of my antiderivative of f will also be increasing from 0 to 1. But then, since my function f decreases from 0 to 3, that means the slopes of the tangent lines have to be decreasing, okay, to 3. But then after 3, the function f increases, so the slopes of the tangent lines to my antiderivative function f have to be increasing. And so if I connect the, you know, if I just draw a function, hold on here, let me get the, if I draw a function, and maybe I'll put it in yellow here. If I draw a function that obeys these tangents, you're going to get this yellow function. That's the flavor of it. And this would be my f of x, my antiderivative. So f is always positive means that f prime of x is greater than 0, right? For all x. Trying to make it. It's not necessarily pretty, but I think it is readable. It's legible. So the fact that our function f of x here is always positive. Okay, that means that the derivative of the antiderivative, capital F prime of x, is always positive. So the tangent lines are positive all throughout the graph. But the tangent lines, because the function f, little function f, increases from 0 to 1, the tangent lines for my antiderivative increase from 0 to 1. But then from 1 to 3, the tangent lines, the slopes, I'm sorry, I don't mean tangent lines, from 0 to 1, the slopes of my tangent lines increase. But then from 1 to 3, the slopes of my tangent lines for my antiderivative function decrease. And then after 3, after x, from when x is 3 or more, the slopes of my antiderivative function increase. Okay, and let me see, Lynn, when drawing the graph of the antiderivative, how should you decide how much to drop the line? So what will happen, Lynn, is for these kind of problems, you will be given multiple choice. Okay, you'll be given multiple choice. They'll give you graphs, and then you will do the multiple choice on that. Okay, is that so really what we did was kind of harder. We graphed the function, our antiderivative function f, from scratch, but you know, the concept is still the same. You still have to, you know. Yeah, I don't think you're going to have anything where you have to draw from scratch. Would that be an interesting exam question, wouldn't it, on the next exam? Draw an antiderivative from scratch. Okay, but you know, I won't think too far ahead. You got to worry about your first test. But are there any questions on this? All right, Lynn's comfortable. And they do this example in the book, but the book, of course, there's a lot of words in the example. This example that they do in the book is actually example 4. There are a lot of words there. I tend to like to use pictures to justify my graphs as opposed to lots of words. But pictures means tangent lines. Okay, like I use tangent lines to help me. Are there any other questions before we? All right,